I'd like to thank the organizers for the opportunity to talk at this conference. So I'm going to give two talks. Both of them are going to be largely expository. And so today I'm going to talk about Gromov-Hausdorff limits and projective embedding. So this is largely work of Donaldson and Sun. And then tomorrow I'll talk of applications to finding Kahler-Einstein metrics. Okay, so the setup is as follows. So let Mn be a complex manifold, and the dimension, the complex dimension is going to be n. And let's say we have an ample line bundle. So which means in particular that this is a holomorphic line bundle, and that there exists a Hermitian metric such that if you take the curvature of this Hermitian metric, which means I have a holomorphic structure, I have a Hermitian metric, so I look at the corresponding Chern connection and look at the curvature of that, then you want the following to be true. If I set omega to be square root of -1 times fh, you want this to be a positive form. So I'll say a few words about this after the introduction. But if you have such a Hermitian metric on a holomorphic line bundle, then you say that L is ample. And then there's a classical theorem due to Kodaira, which I guess Vamsi must have talked about last week, which essentially says that if you have this package of an ample line bundle on a complex manifold, then that manifold ought to be projective, right? And more precisely, one can actually, so what this says is that there exists a natural number such that if you take a basis for H0 of M Lk, so this basically just means the space of sections, holomorphic sections of the kth tensor power of L. And you look at the following map. So X goes to the evaluation of these sections at X. Then this is an embedding. Okay, so firstly, it's not even clear that this should actually give us a well-defined map into the projective space, because if you're unlucky, what might happen is that there might be a point X where all of these sections vanish, right? And then, of course, that wouldn't give you a point in the projective space. So not only does this say that if I raise this to a high enough power, you actually get a well-defined map, but that map is also an embedding. Okay? So now a natural sort of question to ask is, how does this K depend on this data? Okay, so of course, why would one be interested in something of this sort? So one reason is that, mathematicians are always trying to construct moduli spaces. And suppose you want to construct moduli spaces of such polarized Kähler manifolds, which means pairs of Kähler manifolds and an ample line bundle. It's very convenient if you can actually embed that manifold in one particular projective space. Okay, the reason is that algebraic geometers already know how to construct, for instance, moduli spaces of subvarieties of Pn of a given degree. So that's called the Chow scheme, right? And you can also construct the Hilbert scheme and so on. Yeah. So it just means this, that it's a holomorphic line bundle and there's a Hermitian metric. So what is a line bundle? Locally, L is basically like M cross C, right? So you want a Hermitian metric on each of these fibers. So given a Hermitian metric and a holomorphic structure, there's a unique Chern connection. which is compatible with the Hermitian metric and the holomorphic structure. And the curvature of that is basically just given by this formula, right? So square root of -1 times that, you want it to be positive, yeah?
How does omega come in here? K depends only on M and L.
Right. So I'll get to that in a minute. So essentially what you're going to do is to actually construct these sections that are orthonormal with respect to the L2 inner product induced by omega. Right? So the reason is that that is going to interact well with the Gromov-Hausdorff limit. So essentially we are going to consider sequences of these mi's and omega i's, and they're going to
Change omega, does K change? The minimal K change?
right, so it will. Right. So that K actually, I mean, at least the way we construct it, it will depend on omega. Right, so of course, there might be a, so for the entire argument to go through, there might be an omega that sort of gives you the best possible K. Right?
I'll expect that the n-dimensional manifold goes into 12 plus 3-dimensional or something like that, right?
Right, but
this has nothing to do with what you are doing.
No. So I mean, for instance, yeah, in dimension 1, that's for instance true. I mean, everything can be embedded into P3 or something, but that's not the point of this. I actually want these sections to be orthonormal with respect to a certain L2 inner product. Right, so one reason to look at something like this is to try to construct some moduli space of some complex manifolds with some additional data like this L or omega or whatever. The other reason, and that was probably the main motivation for Donaldson-Sun, is this program that had been outlined by Tian on how to use something like this to actually construct Kahler-Einstein metrics on Fano manifolds. So that was the problem that was the main interest of Donaldson-Sun when they actually worked on this. So to formalize this, let me just define the following space. So this is going to be the set of all tuples. So in the background, I also have a churn connection, but I won't often write the churn connection, such that M is a compact complex manifold L is an ample line bundle. Omega, so if you look at this definition of omega, what this actually means, I mean, this guy is actually the representative of 2 pi times the first churn class of L, right? So I take this, I want this compatibility condition to hold, so omega should be in 2 pi C1 of L. The Ricci curvature of omega, so I'll get to this in a minute, but so I want this omega to be a positive form. So such omegas are called as scalar forms. They give rise to Riemannian metrics. I want the Ricci curvature of that Riemannian metric to be lower bounded by -1 and upper bounded by 1. I also want to normalize the volume to be this fixed quantity V, and I just said that omega gives rise to a Riemannian metric, so I want the diameter with respect to that to be upper bounded by D. Okay? So I look at the set of all such tuples. Then the main theorem of Donaldson-Sun basically gives you an effective version of Kodaira's embedding theorem for manifolds in this class. So I'll call this Theorem A. This is due to Donaldson-Sun. I think this was 2011 or something. And it was due to Tian when the complex dimension is 2. Right, so again, for complex dimension 1, this is a classical fact that one can have an effective Kodaira's theorem. You can embed every Riemann surface into, I think, P3 or something, and that just uses Riemann rock, right? So this is a classical fact. So for n equals 2, this was done by Tian, and then in general by Donaldson and Sun. So the statement is as follows. So given n, v, and d, there exists a fixed k1 and capital N, of course, depending only on these three parameters, such that so for all such tuples, there exists an embedding of M into a fixed projective space via sections of this. And in fact, this embedding that we'll give, as I said, will be actually using, so I'll define an L2 inner product, and then the embedding will be via sections that are orthonormal with respect to that inner product. And so the second part is, suppose I look at a sequence which is Mj, Lj, omega j of tuples here, such that these guys converge. So omega j defines a Riemannian metric and hence an actual metric on Mj. Suppose these guys converge in the Gromov-Hausdorff distance to another metric space. So a priori, this is only a compact length space, right? So this need not be a manifold. It's just some metric space where you have a notion of right. So where the distance comes from lengths of curves. And this is not a very strong hypothesis, because there's a classical theorem of Gromov's that if you take such a sequence in this family, then if you pass to a subsequence, you will always get convergence in the Gromov-Hausdorff sense to a limiting metric space, right? So this is not a very strong hypothesis. But then the punchline is that Z is actually homeomorphic to a normal projective variety. Which also sits inside this Pn. Okay, so in fact, along this sequence, by part 1, I have this sequence of embeddings, right? So I can look at images. So for instance, I mean, the picture is that you have this Pn, you have the image of this ayat guy, which I call Mi tilde. Then it turns out that, I mean, you can actually take an algebrogeometric limit. So for instance, I mean, these will have the same degree, so you can actually take the limit in some Chow scheme or something. So you can take some abstract algebrogeometric limit. So in general, of course, that limit might just be a scheme. It might not even be a sort of normal variety. But it turns out in this case, the limit is going to be a normal variety W, and that W is actually going to be homeomorphic to the Gromov-Hausdorff limit. So on the one side, you have a purely metric sort of limit. On the other side, you have a purely algebraic limit. And the second part basically identifies these two, right? So I should make a remark that all this was conjectured by Tian in early 90s. Okay. So it also turns out that in order to prove theorem A, one only has to prove a slightly weaker version, which is called the partial C0 estimate. So this was again conjectured by Tian, and in fact he had indicated how to go from this statement to theorem A. So why is it called, I'll state what this theorem is. It's not quite clear why should it be called a partial C0 estimate, but that will hopefully be clear in tomorrow's lecture. So that has something to do with how this whole setup is applied to the Kahler-Einstein problem, right? So hopefully tomorrow it will be clear why this is called the partial C0 estimate. Right, so here the setup is as follows. So again, let's recall that I'm given a Kähler form in 2 pi times the first Chern class of L, and I guess you have a Hermitian metric such that omega is this. So then one can define an L2 inner product in the most obvious way. So how do you do this? You take some sections, holomorphic sections of the kth tensor product. You just define the inner product. So I'll put a k to remind ourselves that we are looking at sections of L to the k. So this is simply defined as this times k omega to the n by n factorial. Okay, so I should remark that if you look at the kth power of this Hermitian metric, that actually gives you a Hermitian metric on L to the k. So this is a Hermitian metric on L to the k, and the curvature of this is precisely going to be minus square root of minus 1 k omega. So the term that shows up here is essentially just the curvature of H to the pointwise inner product, and then you just integrate. Right. So I mean, good exercise for students is to check that this is actually independent of the holomorphic frame that you look at, right? Yeah. So that's exactly what I mean. Yeah. Right. So then we define the following function. So rho k omega of x. So this is simply the soup of the pointwise norm of sections such that the L2 norm, I should maybe write it like this, is 1. So I look at the set of all sections whose L2 norm is 1, and I take the supremum of their pointwise values at x. So this is of course over S in H naught. Okay, and then you take the infimum of all these numbers. So you define rho of k omega to be the infimum of this as x varies over all of m. So notice that if this is strictly positive, that implies, or if this is bigger than some b squared, this implies that there exists a section such that, so this implies that for all points x and m, there exists a section S such that S of x does not vanish, right? So you're taking the infimum over all these numbers, which means that if that guy has a uniform lower bound, you would at least be assured that this map is well defined, right? So you would at least have one section that, I mean, given any point, you have at least one section that does not vanish there. So that means that this map should be well defined as a map into the projective space. So then the theorem of Donaldson-Sun is precisely that in this particular, with this particular family of manifolds, you actually have a uniform lower bound on that function. So again, this is due to Donaldson-Sun and then Tian when n is 2. So maybe if this time I'll indicate why it's slightly an easier problem when n is 2. And it actually, I mean, this was sort of the central problem in the field for about 20 years before it was finally resolved. So again, there exists a k naught, which again depends on this, on these three parameters, and a b such that for all ml omega, this is lower bounded uniformly. Okay. So any questions? So maybe for the rest of the talk, I'll first maybe give you a brief background in Kahler and Riemannian geometry, because I guess this is mostly an audience of analysts. So I'll give a very quick overview of some important terms in Kahler and Riemannian geometry. And then maybe I'll give a brief outline of this proof. So I won't have time to actually go into the proof of Theorem A. It requires some work even once you establish Theorem B. But as I said, I mean, to a large extent, that was sort of indicated already by Tian's work in this dimension 2. Right? So the hard part was really obtaining this in all dimensions. Right, so let me give a brief background on Kahler manifolds. Right, so I start with a compact Kahler manifold. So that means I have a compact complex manifold with this 2 form. So omega is a 2 form such that locally there exists holomorphic coordinates z1, zn, such that the following holds true, that omega can be written as square root of minus 1 by 2 gij bar dzi wedge dzj bar with the first condition is that this, I mean, this is basically a local matrix of functions, and you want this matrix to be Hermitian and positive definite. Okay, so the Hermitian part basically tells you that omega is a real 1-1 form, and this positive definiteness basically tells you that this is positive for all tangent vectors of type 1, 0. Right? So if you have seen a bit of complex manifolds, this is basically, I mean, the positive definiteness gives you positivity of this form. But the Kahler condition actually says that this omega has to be not only any 2 form, but a closed 2 form. So the second condition is that d omega has to be closed, or d omega has to be 0, which is actually equivalent to the following statement that locally Gij is essentially given by the Euclidean Kahler form up to an error of order z squared. Right? So essentially, if you look at the Taylor expansion of these functions, it will have, of course, you can always sort of use a unitary transformation because it's a Hermitian matrix. So you can use a unitary transformation so that at a particular point, you can make it Euclidean, but then there'll be some first derivative terms, right? So it turns out that if d omega is 0, you can also make another change of variables to essentially do away with the first order terms. Okay, then as I said earlier, this will induce in a natural way a Riemannian metric. So for that, I mean, there are various ways of seeing how this gives you a Riemannian metric, but maybe in local coordinates, the easiest way is as follows. So, so locally, the metric will be given, of course, by something like this, where now I choose these coordinates xi, xj, so that zi is xi plus square root of minus 1 xn plus I gives me my holomorphic coordinates, right? So then this guy can be written out in terms of these Gij bars, and if I did this calculation correct, it should be something of this sort. Okay, or maybe there's a minus sign here and no minus sign there. But anyway, so you can, in these special coordinates, you can write down exactly what the matrix of your Riemannian metric should look like. Okay, so now given a Riemannian metric, one can talk about its curvature. In particular, one can talk about the Ricci curvature. So just like omega in a canonical way induces a Riemannian metric, the Riemannian Ricci curvature is also canonically induced by what is called as the Ricci form of omega. Okay, so this is induced by the Ricci form Okay, and the Ricci form has a very nice formula. It's basically minus d bar, or right, minus d bar log of, so maybe just to be consistent, I should put a minus square root of minus 1. Okay, so if you're not comfortable with this, you can also take the determinant of this matrix Gij bar. Right, so it turns out that this is in fact a global 2 form. I mean, if you stare hard enough, that becomes sort of obvious, because if you change coordinates, this determinant will basically be multiplied by the mod squared of the holomorphic Jacobian. And I mean, so that means this will be transformed by the holomorphic Jacobian times the holomorphic Jacobian bar. And then D, once you take log, this separates, and then D kills this guy, D bar kills this guy, right? So this is in fact a globally defined form, okay? So this is nice. I mean, some of the power of Kähler geometry actually comes from the fact that the Ricci curvature has such a nice formula. I mean, if you have some experience with Riemannian geometry, you know that in Riemannian geometry, the Ricci curvature is a much scarier looking beast, right? But at least geometrically, there's actually a very nice interpretation of the Ricci curvature, and this sort of plays an important role. So if you look at the determinant of Gij bar, so this actually turns out to be the volume element. So the volume element given a Kähler metric, I mean, of course, what is the volume element of this matrix, or sorry, of this metric? It's basically square root of determinant of G, right? And from this expression, you can easily see that that is basically going to be the determinant of Gij bar, okay? So essentially, this guy is going to be the volume form, and then locally, this is an expansion. So of course, to 0th order, this will agree with the Euclidean volume form. And the first sort of error comes precisely from the Ricci curvature. So you can write this as square root of -1 Rij bar dzi dzj bar. And then these coefficients basically show up when you take the Taylor expansion of the volume element. And then of course you have something that's of order ZQ, right? So the infinitesimal sort of change in volume is measured by the Ricci curvature. So it's not very surprising that some curvature should show up when you try to measure the infinitesimal volume, because if you, for instance, look at the sphere, if you look at geodesic balls, then geodesics on the sphere tend to sort of move towards each other. So the corresponding ball will have smaller area than a Euclidean ball. And so that's smaller because, I mean, sphere is positively curved, so that's why you have a negative sign here, right? So you should think of the Ricci as sort of the infinitesimal distortion of the volume element. So what we really need are some consequences of a Ricci lower bound, and of course the diameter being bounded by D and the volume n factorial times capital V, right? So some consequences of this are as follows. So there's one very geometric consequence, which is based on just this simple observation that the Ricci curvature basically decides the infinitesimal change of the volume element. So integrating that observation, you have the famous Bishop-Gromov inequality, which says that there exists a constant depending on the dimension and on these parameters, such that for all points on the manifold and for all radii less than the diameter, if you look at the volume of the ball of radius r, so now when I say ball of radius r, I'm talking about in the metric that we are considering, so in this case the metric omega, then this is lower bounded by c times r to the 2n. Okay, so the volume of small balls aren't too small, right? So they're at least as big as the Euclidean volume up to a certain factor. So of course this 2n is because my n is the complex dimension, and so the real dimension is 2n, right? So this is one very geometric consequence. The second thing we need is the so-called uniform Sobolev bound. This is probably due to a lot of people, but sort of the standard reference is due to Kroc. And so if you have Ricci lower bound, you have a bound on the Sobolev constant. So there exists a CS which again depends on the parameters that you have, such that for all f smooth, you have an inequality that looks like L n by n minus first norm of f is bounded by the Sobolev constant times the L2 norm of the gradient squared plus the L2 norm of f squared. Okay. So again, if you taken a course in analysis, you would be, I mean, this exponent is usually 2m by m minus 2, or sorry, m by m minus 2 or something, and then m here is 2n, because that's the real dimension of our manifold. Right, so an important consequence of this is that one has a priori estimates on how big these sections can get. So a consequence using a very standard technique in geometric analysis, namely Moser iteration. So essentially you have constants k1 and k2, again depending only on n, d, v, such that if m L omega belongs to this class and S is a section of the kth tensor power of L, then in fact the L infinity norm is bounded by the L2 norm. So again, all the norms are measured with the Hermitian metric h to the k, right? So I'm not writing this, but whenever I'm considering the bundle L to the k, I'm considering the corresponding metrics, right? So h to the k, or when I'm integrating to compute the L2 norm, I'm actually looking at integrating with respect to k omega time to the power of n, right? So one also has a gradient estimate Okay, so at least for holomorphic functions, things like this should be familiar, right? I mean, they essentially follow from the Cauchy integration formula that once you have, I mean, because if this is a holomorphic function, it's given essentially by integration on a certain ball, and then you can measure the L infinity norm by the L2 norm, right? And similarly, pardon? Yeah, M is always compact for me, right? Right, so at least for complex analysis, this should be familiar. But the trick here is, of course, that that S is not a holomorphic function, but it's actually a section. And so in fact, this little covariant derivative also involves, for instance, the Chern connection, right? So the way to prove this is to obtain differential inequalities for mod S and for something like this. So essentially, I think for mod S, if I remember, you basically obtain an inequality of this type or something, right? And then basically, once you have this inequality, a standard package called as Moser iteration gives you estimates of this sort. The proof for this is slightly harder because you need to compute this, which is a sort of Bochner formula. Again, it's a standard calculation in geometry, but if you aren't familiar with this, this requires a bit of hard work. So again, one obtains a differential inequality for this, and then by the standard package of Moser iteration, one has that estimate. Pardon? Right, so these constants are actually independent of k. So maybe let me make a remark that these constants basically just depend on this Sobolev inequality. right? And the fact that the curvature of the Chern connection is basically the Kahler form that we have, right? So, so it depends on that. And in fact, so of course, why is the Sobolev constant sort of independent of this K? So let me make a quick remark about rescaling, because we are going to do a whole lot of rescaling in the rest of the talk. So the point here is that suppose you have your metric omega and you rescale to k omega, right? So the idea is that in the Bishop-Gromov inequality, the constant actually doesn't change. So essentially, I mean, what is happening when you change omega to k omega? The lengths are getting scaled by a factor of root k, but the volume is also getting scaled by a factor of k to the n, right? Because the determinant of Gij plays the role of the volume element. So the volume is getting scaled by k to the n, the lengths are getting scaled by root k, and then if you actually write this down, if you consider the ball in the metric k omega, its volume will be scaled k to the n times whatever, but then you're considering your lengths are also getting scaled by root k, so that will give a factor of root k to the 2n here. So this Bishop-Gromov non-collapsing constant is actually independent of rescaling. Okay, so C is independent of rescaling, and in fact in 2, CS actually gets better. So I think if you do a similar rescaling argument, I think the factor that comes from here sort of gets cancelled by the factor that comes from here, but then you have a additional factor here which is actually helpful. So when k is big, that factor is actually going to be small. Okay, so which means that your Sobolev constant that worked for omega also works for k omega. Okay, so uniform Sobolev inequality independent of k. So in fact, crucially, these estimates, these constants actually do not depend on k. Okay, so that's a very important part of their argument. Okay, any other questions? Right, so I guess I have around 15 minutes or something. So maybe let me give you a quick outline of the proof of this theorem. So let me leave it here. So the main sort of heuristic is that when you raise your line bundle to the kth power at the metric level, that means that you're scaling your metric by a factor of k, right? So let's see how that actually helps us in proving something of this sort. So I'll first prove this in the case when M is a single manifold. Okay, so let's not worry about this space k n dv that we have. Let's just worry about a single member in that family. So this is essentially the first step in proving Kodaira's embedding theorem, right? Given such an M with an ample line bundle, you want to say that there is a well-defined map into some projective space, right? So let me remind you how that proof works, and then we'll try to generalize it to a family version. Right, so the main idea is as follows. So here we have our M. So let's look at a fixed ball. Okay, so I choose this ball of radius 1 in the initial metric omega, such that omega is almost Euclidean in this ball, up to, I mean, remember my definition of Kahler manifolds. So, so this thing is almost Euclidean up to the second order. And of course, this can always be done locally, but by rescaling omega initially, I can assume that I can actually do it in a unit ball, right? So now the point is that this is actually, at least set theoretically, the ball of radius root k in the metric k times omega. So if you're scaling the metric by omega, so if you're making the metric really big, then as you go to the edge of this ball, you're actually covering a lot more distance, right? So the same ball becomes a ball of radius approximately root k, I mean, or exactly root k in the metric k omega. So now the idea is that, so essentially, I mean, what happens when you take a rescaled metric, it's like I'm taking a magnifying glass and zooming in on this ball, right? So that is essentially the meaning of taking a rescaled metric. So once I take the rescaled metric, this is almost like a Euclidean ball of really large radius. Okay, so remember, what is my goal? In order to show something of this sort, given this point P, I have to exhibit at least one section whose value at this point is pretty big, right? So that's the goal. So goal, there exists a holomorphic section of a large enough power such that the value at this P in the relevant norm is at least, let's say, half. And I guess I also want the L2 norm to be 1, but it's enough if I sort of manage that the L2 norm is, let's say, smaller than 100 or something, right? Then once I rescale this section, I'll get the rescaled section is, I mean, the value is bigger than maybe half, I mean, 1 by 200 or something, right? So that's the goal. So I can also choose this ball so that L restricted to this ball is basically trivialized. Okay, so I can always have a local trivialization, and by rescaling I can assume that I have a local trivialization on this ball, right? So now the point is, on this Euclidean ball, there is already a Hermitian metric, which is basically the Gaussian metric. Okay, and my Hermitian metric h to the k is actually quite close to this Hermitian metric, right? And then if I look at for instance, the trivial line bundle on this, I have a trivial section, which is basically the section 1 everywhere. So I take the trivial section, I mean, trivial, non-trivial section, in the sense that the trivial section which is not 0 everywhere, but so trivial section sigma naught, such that the norm in this metric is approximately at, let's say, P is approximately 1. And I basically cut off, so take a cutoff function, because the idea is that I want to get something global on M. So I have a local model section here. I just paste it onto this, and the way to paste is, of course, by choosing a cutoff function and multiplying it by some cutoff function. So take a cutoff function beta and consider the section beta times sigma naught. So I'll call this sigma 1. Okay, so now the problem with sigma 1 is that it's no longer holomorphic, right? Because you have introduced a cutoff function. So in fact, the d bar of sigma 1 is going to be d bar of beta times sigma naught, right? But in fact, if you are careful with our choice of the cutoff function, one can actually choose beta so that's basically because this ball has a huge radius. So, I mean, cutoff functions normally, their gradient decays like 1 over the radius. So here the radius is root k, so the gradient I can make it very small. And also this section is pretty, since it's a Gaussian section, it actually decays very rapidly near the boundary. So I can choose beta so that the L2 norm of this is small. So that means that this guy, even though it's not a holomorphic section, it's an almost holomorphic section in an L2 sense, right? And then basically this Hörmander package so actually it's even easier than, I mean, Hörmander originally had worked this out for, I guess, Stein manifolds or pseudo-convex domains. But here, because we are working on a compact manifold, this is actually, in fact, even easier than his, his work. So Hörmander technique implies that you can add a correction, eta, such that S is actually a holomorphic section of this. Right? And because sigma 1 is almost holomorphic in an L2 sense, it turns out that the norm of this genuine holomorphic section, of course, it will no longer be approximately 1, but you can always make sure that this is bigger than half. Okay, and similarly, you can also control the L2 norm. So that basically tells you how, given a single manifold, how you can construct a section which does not vanish at a particular point or is not too small at a particular point. So now, when we have a family of manifolds, unfortunately, so I mean the key point here really was that there is a certain scale where your metric looks Euclidean. But now, suppose you have a family of such manifolds, unfortunately, there's no common scale at which your geometry looks Euclidean. So how do you do this for? So I'm going to sort of proceed by contradiction. So the actual proof requires some more work, but I'm going to present a sort of simplified or a weaker version of their result, in which I can proceed by contradiction, and I can only look at sequences here, right? So to go from this to their actual theorem, you need some additional technicality, which is not that serious anyway. So I'm going to proceed by contradiction. That is, there exists a sequence Mj, Lj, omega j, and these points pj's in Mj. So of course I want all of these to belong to k, n, d, v, such that this function that I defined at pj gets smaller and smaller. Okay, so then I want to get some contradiction so that at least that proves their theorem for sequences. Okay. So again, what is the goal? So the goal is to, for j big, we want to find a section S, which is a holomorphic section in Mj, Lj to the k naught, such that the value of this section at the point Pj is, let's say, bigger than half, and the L2 norm is under control. Okay, so if I can do that, then I get a contradiction, right? Because then these numbers cannot actually go to 0. So as I said, the disadvantage here is that there's no common scale where things look Euclidean. But I said that there's this abstract theorem due to Gromov, which tells you that one can extract a subsequence which converges in this Gromov-Hausdorff topology to a metric space. So up to a subsequence, this mj omega j, or the metric defined by omega j, that converges in the Gromov-Hausdorff topology to this compact metric space. So let me just draw a picture. So what might happen is you have these points or these manifolds mj's which sort of converge in the Gromov-Hausdorff sense to something that's a priori only a metric space. So the idea is that along your sequence there might be some, for instance, some curvature concentrating near M, which means that in the limit you shouldn't expect to get something that's a smooth Riemannian manifold, but so in the limit you expect something that's singular, and the way to analyze regions close to these singularities, so this is a standard notion in geometric analysis, is to consider what are called as tangent cones. So again, that's the same philosophy as this. You just take a microscope and look very close to this region, right? So it turns out that there is a certain scale where it's no longer Euclidean, but so there exists a certain scale k, so that if you look at a ball of radius 1 in the original metric, so this is Pj, you look at a ball of radius Pj in omega j of radius 1, and look at it in the scaled metric k times omega j, that actually looks like not Euclidean, but it looks like a metric cone. So it's going to look like this. So this is probably a bad picture, but the point is that these guys, I mean, this is some other metric space Y, which is called the link of the cone, and your so this ball in this rescaled metric is going to look close to a region in this metric cone C of Y. So this is topologically, this is basically just some other topological space cross 0 to infinity, but then you basically, so this is like a cylinder, but then you squish one of the ends together, right? So you have an equivalence relation that this is equivalent to, and this is a sort of canonical metric depending on the metric on Y. So the metric is defined via the cosine rule. And what is more, in this situation, there will actually be a form, omega c, which is minus dd bar of mod z squared, where mod z is the distance from the tip, such that on the regular part of this cone, so maybe I'll explain what the regular part is. On the regular part of this cone, the metric induced by the scalar form is the same as this metric. Okay, so the regular part is basically, I mean, Y, under good circumstances, Y is going to be at least a C1 alpha manifold away from a codimension 4 set, and those are these singular points. And then the cone is also going to be smooth away from the vertex and these rays, right? So away from these bad rays, your distance can actually be recovered from this scalar form. So this is a situation that's very similar to the situation here, where the standard Euclidean Kähler form is basically the curvature form of this Hermitian metric, right? So essentially, one tries to do that construction with this, but there are a couple of added technicalities, so maybe I'll mention them and then stop. So the added technicalities are, of course, that you have some singular points. So one has to, when one considers that cutoff function, one also has to sort of erase out this region and also the vertex region. So remember, we wanted to estimate the section here, but essentially by using Hörmander's technique, we'll only be able to estimate the section somewhere here, very close to the tip. But then how do you go from here to here using the gradient estimate for holomorphic sections that I erased? So if you know that it's quite big here, even at the tip it'll be quite big, right? So that's one technicality. The other technicality is that if you look at this sequence of line bundles LJs, they'll converge to some line bundle on the regular part of this cone, but that need not be the trivial line bundle, okay? Even though the curvatures converge, so even though one can show that these omega j's or scaled versions of these omega j's converge to omega c. So this is because even if you have, for instance, a flat connection, that doesn't mean that your connection itself is small, right? And the reason is that this Y might have some complicated topology. So there is an additional topological obstruction. So you have to take care of what is called as, that's the holonomy obstruction, and one has to, also take care of that. And that holonomy part is not there when n is 2, because when n is 2, the link is going to be smooth, okay? So one doesn't have this additional topological obstruction. So maybe, sorry, I went a bit over, but I'll stop here. Thanks. Yeah.
So can this method of producing sections which are non-zero, I have this long-standing, can you prove Weierstrass theorem by L2 method? So if in a planar domain, simplest scalar manifold, but non-compact, you want to construct function with specified zeros and no other zeros.
Right.
Can you do that by some variation of this method, by scaling the metric and something and taking Debraj data, which is very small?
Yeah, probably. I thought Weierstrass is sort of a more complicated but lower dimensional case of basically the L2 method. So yeah, maybe one can.
That you don't want. I can put zeros anywhere I like.
Right.
I have no guarantee that I'll not have any other zeros.
Right.
So this seems to be a way in which that can be done, perhaps, right?
No, but even here you might have zeros somewhere else, right? Because it's not. I know that at this point my section will be big, but it doesn't mean that the section might not have a zero somewhere else, right?
Do you know, is there a way of doing that?
No, I don't know, but yeah, that's an interesting question, right?
Thank you.
Okay, thanks.